PDAC classification using R. What is PDAC and why is it important to detect early? PDAC stands for pancreatic ductal adenocarcinoma, which is the most common form of pancreatic cancer. It's very difficult to detect at early stages, and when detected late, it has a 5-year survival rate of less than 10%. The data that I used for this project was from a research paper published in December 2020 that created a urinary diagnostic test for PDAC. The urinary biomarkers they used were creatine, LYVE1, Reg1A, Reg1B, and TFF1. Additionally, it provided some basic background and information on the dataset itself and also the research paper. The target variable diagnosis was split into 3 groups to start: healthy control, benign being someone with another condition impacting the pancreas, and PDAC. The goal was to predict whether or not a subject had PDAC or not. To do this, I then later had to group the healthy control and the benign individuals into one group called healthy and then leave PDAC alone for the binary classification. I mostly explored the data by diagnosis type. I first looked at the averages for each biomarker by diagnosis type and then looked at how diagnosis was split by gender and how the age of subjects was distributed. To take a closer look at each biomarker, I created QQ plots. This showed that each biomarker I found, they were mostly heavily right skewed. I then wondered how this distribution was skewed for each biomarker by diagnosis type. The density plots show that. The data that needed to be transformed was Reg1A. This was a measurement that was only assessed in 306 of the subjects, so I decided that KNN regression would be the best way to impute the missing values. This was because using mean or median would damage the model because of distribution of biomarkers for each diagnosis type. Because all of the biomarkers were skewed to the right, I also had to transform them using log base 10. A KNN classifier, support vector machine, and a random forest. The KNN classifier first run through performed at 86% accuracy. The support vector machine also performed the same and also predicted the exact same confusion matrix. The random forest did not perform as well. And evaluate the models, I decided to build ROC curves and also calculate area under the curve. Despite the random forest performing much worse for the initial pass, it actually had a very high ROC and high AUC compared to the KNN model. The support vector machine also performed pretty well. I built the ensemble model by calculating and training a model using tenfold cross-validation and adjusted parameters for each model. For the KNN model, I tested for k between 1 and 30. For the support vector machine, I tested cost values from 1 to 20 with corresponding sigma values being 0.01 or 0.1. That was the default for the previous model. And the random forest was tuned for mtry, which is the number of variables randomly sampled as candidates at each split. I then used the model to predict the values for diagnosis and used a majority vote to decide the classification. To do this, I used an if-else function to compare the values. Only values that the only two values needed to match to pass, so it simply goes through and checks against each of the k&n results. And then if the k&n doesn't match the support vector machine or the random forest, by default, the support vector machine and random forest would be the same. So that's kind of how it went through and calculated the majority vote. The first run through of the ensemble model did not provide as high of results as I was anticipating. But then I ran a tenfold cross-validation, and it was determined that it actually did have a higher accuracy and kappa statistic on average than the other models. As you can see, the ensemble model is higher than the other three. To summarize the findings, the ensemble model performed better than the individual models. That was shown through cross-validation. The random forest performed better than the other two individual models, the k&n classifier and the support vector machine, and that was also shown through the ROC and AUC as well as through cross-validation. The lessons learned from this is the importance of cross-validation. Ensemble models are also very computationally intensive, but they yield higher results. I believe that more data is definitely needed to create a larger testing set and also improve the model itself. I think that was one of the biggest shortcomings of the data set that I was using, and I hope that more data is made available in the future to provide better analysis